Hi everyone, this is Nick Richard from RadWave. Today I wanted to announce the release of RadWave 2.1.0, which adds some cool new features to the RadWave Explorer application. Before we dig into what these features are, I just wanted to do a quick recap of what RadWave is and what we're trying to accomplish. So RadWave is aimed at helping out with the Breakthrough Listen project and lowering the barriers to entry to make it easier for more people to help look at and process this data. So Breakthrough Listen specifically is the largest ever scientific research program aimed at looking for civilizations beyond Earth. And the scale of it is very large, but one of the unique aspects of this program is that they've created and provided this open data archive where raw data from the telescopes used to make the observations has been made available to the public. So anyone can go in here, can look at data from these different observatories, can specify what type of data they're interested in, and what specific targets that they want as well, and download this data. Now, the individual who is chiefly responsible for starting this program, his name is Yuri Milner. And one of the things that he was quoted on is saying that the idea is to bring a Silicon Valley approach to the search for life. And by that, he meant an approach that's transparent, that's innovative, and that uses the power of crowdsourcing. So while at this point, the transparency has been made available through this open data archive, the innovation and the crowdsourcing in particular has not really been leveraged. And that's what RadWave is really hoping to provide a means to accomplish. And the way RadWave does this is by making a simple application so that users can more easily find data in this open data archive, process it, and explore it interactively. So let me do a very quick overview as to how that's done. So here we have the RadWave engine application. So on the left sidebar here, we have a list of all the different objects that were observed by the Green Bank telescope for the Breakthrough Listen project. And if you click on any one of these, what you'll see here is a plot of the times and frequencies that this object was observed at. If you zoom in here, each of the blue boxes outlined in red corresponds to a single file. And if you control click on it, you'll select which one that you're interested in processing. So you can select any ones that are contiguous in time or frequency. As you can see here, the size of each file can be fairly large. So this one is about 4 gigabytes. In general, these can be as much as 17. So you're going to want to have some amount of external hard drive or hard drive space available in order to do all the processing that's required. Here you can select all the different configuration options for processing this raw data in order to have something to look at. So we can enable audio output. So this will process the data in such a way that you can extract small portions of it in frequency and time in order to listen to the different signals that you're able to observe. There's also options to select the frequency resolution. So you'll want to choose a frequency resolution that's relatively on the same order of the bandwidth of the signals that you're interested in observing. And then there's some options here that are related to some minutia of how the data is formatted. And so once you've set up how you want to configure it, you just click Start Download and Process, and it'll kick off and start doing its work. This can take a non-trivial amount of time to run just due to the volume of data and the type of processing that's required of it. So I'm going to abort this right now. And then we can pick it up later on. Now, once you've actually processed all the data, we can then open it up in the RadWave Explorer application to analyze it. So let's do that now. So here we have the RadWave Explorer application. So with this application, we've already downloaded and processed the data, and now we have these individual collections that we can then view. So this one here corresponds to object TIC 159.107.668, and specifically at the 845 megahertz center frequency. So with this particular application, we can use the mouse to zoom in and out on different areas of the spectrum in order to see what's there. We can also use these sliders to change the min-max power levels to improve the contrast so that way you can see the signals come out in the spectrogram. So now we can see some more content that's here. We can also change the center frequency, the time, the duration that's in view, as well as the bandwidth with these sliders. And our primary objective with the breakthrough listen data is to label it, right? So one of the largest objectives of crowdsourcing is to be able to actually go in and get human eyeballs on this data and detect not just the SETI candidate signals, but also the interference, receiver artifacts, natural phenomena, because as it is, even if we don't find SETI candidates, this is real radio astronomy data that's pointed at objects that the SETI community believes to be places for habitable life, or of sort of major radioastronomical significance. So even if we don't detect signals from extraterrestrial civilizations, we could easily detect signals that are natural that would have a large impact for our understanding of the universe in general. So let me just go over some of the new features that have been added into this application in the RadWave 2.1.0 release. So one of the things I've done is re-architected how the mouse controls and layers are available from a software perspective to allow future plugins to be made by third parties. So I hope to open source that plugin software development kit for other developers who want to contribute here and provide some cool functionality. So for some of the things that have been added in already, we now have tag bounding boxes. So as people create tags to label portions of the spectrum, you can toggle those on and off. And if you right click on it, you can change the color for each of these different tags, so that way it's easier on your eyes. We also have the ability here to click on any one of these tag bounding boxes and see information about it. We have like the basic details of the time and frequency of the bounding box itself, as well as the primary label and secondary label that the user selected when they created this tag. Users can also provide a description of it. Currently, we don't have support for users. There's a bunch of, GDPR and data privacy regulations that RadWave would need to adhere to in order to make that possible. But the hooks are in place to make that possible once RadWave gets to that point. And also, in order to improve the data quality, I have hooks in place to enable upvoting and downvoting of the tag, so that way people can agree or disagree upon this, and in order to provide some validation that the tag is in fact labeled correctly, as well as having hooks for comments on it. So there can be discussions about each individual tag, and we can provide a mechanism to educate people as to what things are so they can learn and improve over time. As if we zoom in more, let me see here. We can show how candidate tags can be created. So let me do this real quick. So here we have some sort of signal. It appears to be slightly Doppler shifted, but that could be due to a satellite transmission. So if we click the tag button here, then we can manually add tags and create them. Here you can set the primary ID. So I would anticipate this being interference, some sort of man-made satellite spacecraft, just because it's Doppler shifted. But in reality, I don't really know. See me type slowly there. And at this point, we can also edit the tag. By this, I mean change its boundaries. Sometimes it's hard to set things correctly when you're first doing it. So this allows you to modify the bounds of it. Another feature that's been added here for these candidate tags is the ability to do some raw data processing. So at this point, we have two raw data processors that have been made available. The first is natural audio. So this does effectively single sideband amplitude modulation, demodulation processing, in order to extract audio that you can then listen to, as well as a no-op to a file. So this doesn't actually do any sort of filtering or demodulation, it just saves it straight to a file. We'll get into that in a moment. But for the natural audio processing, let's click start on this one so we can see what this actually looks like. All right, so here we have this window that gets created, and we can get a better look as to the content here. So this window has a few functions that are new. The first is the ability to reprocess the raw data for this small time frequency window, with a different frequency and time resolution. So as you increase the FFT order, for those who are familiar with digital signal processing, FFT is a fast Fourier transform. And that'll change how this signal looks. So the smaller your FFT order, the coarser the frequency resolution and the finer the time resolution. And as you increase it, it goes the other way around. In this case here, this signal is extremely short in time, and so we'll want the finest time resolution that we can get with this particular signal here. And now we can sort of zoom in on it and start to get a slightly better idea as to how this thing is structured. Once we have it there, we can click the play button in order to listen to it. So here you can hear that there's some static at the beginning and end of the signal. So at this time here beforehand and this afterwards, there's static just because there's no actual transmitter active. But during this time, you hear a little squeak and then a little bit louder static that corresponds to this appears to be a digitally modulated signal. So we're able to do all that, which is kind of neat. At this point here, we can then accept the selected tags. It'll save that. It'll store a shareable image in a directory. So that way you can bring it online or whatever. All right. So now let's look at another signal here. I'm going to disable these tag bounding boxes for a moment so we can see something kind of cool. So just like before with this natural audio processor, we can extract these two signals that appear to waver a little differently than each other, but sort of with a similar-ish behavior. And we can look at the spectrogram in more detail. So this takes a little bit more time to do just because it's a larger volume of data. All right, so we'll update this plot and I'll set this to about 7, I think is what looks best. And here we can see the two signals that waver in frequency over time. What we're looking at right here is actually the Stokes parameter. So this corresponds to the total intensity of the signal. And what that means is that, so the Green Bank telescope, so let's get a picture of that just so you can see what's going on. So the Green Bank telescope is this telescope right here. So it's a very large, like very, very large reflector. It's located here. And then the antenna feed is up here. And this particular antenna is set up in such a way that it actually has two different feeds that are shaped in an X. So most antennas that people are familiar with that just stand vertically up and down, right? So this would be like an antenna on an old car. It just goes straight vertical. A vertical antenna is great at receiving signals that are vertically polarized, so that are transmitted by an antenna that is also vertically polarized. So as the electrons move up and down on the transmit antenna and they propagate over to a receive antenna, if that antenna is also vertically polarized, it's oriented the same direction, then it gets received well. Now, if your receive and transmit antennas are perpendicular to one another or orthogonal, then you're going to lose a lot of, you basically won't receive as much energy because the antenna is oriented the wrong direction. The electrons can't wiggle vertically because it's horizontal. And so in that case, you need to shift your receive antenna to match your transmit antenna. So you always want your transmit and receive elements to be oriented the same way in order to get the maximum receive power on your receiver. But when we look for signals that are extraterrestrial in origin, that we're not in control of transmitting ourselves, we really don't know what the polarization is going to be. And so in those cases, what we can do is actually use two different antenna feeds that are oriented perpendicular to one another and receive both components. And so that's the way a lot of these radio observatories are set up. So let's go back to our picture here where we see this total intensity. So this is the total power that is received from both antenna elements. But because of how we're doing our processing with RadWave, we can actually look at the 4 different Stokes parameters that are commonly used in radio astronomy. So the Stokes Q parameter is polarization along the x-axis, so horizontal. And if we update this, we can see that these two signals actually have different polarizations, which is something that you really can't tell if just looking at the total intensity. And this gives us an idea as to the actual physical structures that are transmitting the signals. At least that's my interpretation of it. I'd love to be corrected by someone who's more in the radio astronomy community. But yeah, so as we change the power here, we can start to see the negative peak in power of this Stokes Q. And as we go over here, we can start to see the positive peak in the Stokes parameter here. We can do the same types of processing for linear polarization along the 45-degree axis. So this is Stokes U parameter, and we can see that they both have a positive U component, as well as circular polarization. So circular polarization can correspond to a helical antenna, which is used on What is it used on? I think it's used on Voyager Space Probe, if I recall correctly. So yeah, there's some really cool visualizations we can do now that enable us to not just look at the power that's being transmitted by these signals and how they vary in time and frequency, but really start to dig into how the emitters are structured. Okay, cool. So we're just going to leave this one alone. We'll reject this tag for the moment. But we can go back here and we can look at a no-opt file. So with this process, we can now output data in both SigMF and complex float 32-bit format. I'll be honest that the complex float 32 really doesn't provide any benefit over SigMF because it provides that as well, and the SigMF provides you some additional metadata. And you can select where it's going to output the file to, what the name pattern is going to be. So if you wanted to put something here, you can. And then you can close this and start the processing. And so there you go. Yeah, so that file can then be opened and processed using Python or C++ or whatever it is, Java, whatever it is that you're interested in utilizing. So for some other features that have been added here, the one other one that was kind of major is being able to change the spectrogram direction. So now, depending upon whether you're doing a very fine frequency resolution or a very coarse frequency resolution, it can be helpful to view the spectrogram horizontally or vertically in order to have appropriate resolution for your screen. So you can just better tell what's going on in the spectrum. So that's available. You can change the minimum and maximum audible frequencies for all of the audio demodulation. So for the natural audio, basically it's mapping the maximum frequency that you're observing to this maximum audible frequency and the minimum frequency to this minimum audible. So that way it's in a pleasant range for you. I really can't stand high-pitched noises, so I keep this kind of low. But yeah, so those are all the primary features that have been added to the RadWave Explorer for RadWave 2.1.0. I would love some feedback from anyone who's interested, and hopefully in the next round, I'll also be providing the plugin SDK so other people contribute to some controls here. All right, thanks so much for listening. Bye.